goes again with a memory refresh, and yeah, that's true. So what have we seen last week? We basically saw sorting algorithms, and the most known ones we already seen: bubble sort, merge sort, and counting sort. And we have discussed that in order to analyze the time complexity, we need to something universal, independent from the hardware, and that's where we introduce the Landau symbols, for example, the big O notation, theta notation, and also omega notations. And then we dove into the master theorem, and we learned how to use it to solve linear recursive functions. And also, finally, we compared all the sorting algorithms we learned about and discussed the best use cases for each. And today, we will build on that foundation and delve into a new topic, which is graphs. I hope everyone is really interested about it. Well, first of all, how did the whole graph theory start? And in order to answer this question, let's travel back in time to 1936 and meet the great mathematician Leonhard Euler. Well, Leonhard was living peacefully in Basel, creating great mathematician equations, and building also the exponential notation, and till he heard about the Königsberg Bridge problem. So this is a city in Russia, and basically in this city there were 7 bridges connecting different parts of the town, and the problem was, can a citizen walk through the town in such a way that each bridge will be crossed exactly once? And I've brought some possibilities. Let's try to explore them together. For example, this one, they start from this bridge, then go through this one, through this, and this, but then at the end, the 7th bridge isn't really used. And let's see another possibility. At the end, also here, the 2nd bridge isn't used. Let's explore a 3rd possibility. Maybe it will clap this time, but sadly it's not, it won't. Here, the 3rd bridge isn't also used. The thing is, even if you keep brainstorming till next week, such a walk you won't really find. And how did Euler actually know that such a walk isn't really possible? He abstracted the city layout into a graph, and he concluded that such a walk is only possible if the bridges have even degrees. Yeah, and if we observe the resulted graphic, the graph, we see that here, for example, this node has the degree 3 because it is connected to 3 edges. Also, this one, its degree is 3. This one is actually 5, and this one is 3. So all of them have odd degrees, and therefore such a walk is not really existing. And just by this conclusion, Leonhard Euler built the foundation of graph theory, and he wrote his very first paper on that, concluding that the Königsberg problem is only solved, or it's not really solved, and actually such a walk through the bridges is only possible if and only if bridges have even degrees. And now let's go back in time to present and see what is exactly a graph. Well, simply, a graph, as seen with Euler's abstraction, when he transformed the field into a simple graph that has vertices, aka nodes, and also edges. So if we put that nicely together, we will have a graph denoted by G, which has a set of V edges and set of V nodes, and E edges. Also, we can represent it as a graph right here, or we can also write it down as a set. For example, this graph that has 5 nodes. So V includes 1, 2, 3, 4, 5, and E has all the edges that are connecting the nodes. Now, are all graphs the same? Is every graph a normal graph? And the absolute answer is no, because there are many types of graphs. Yeah. First one is directed graph, which is, as usual, a set of nodes connected by edges, but with directions this time. So, for example, we see that there is an edge between B and A, but this is written as BA and not AB, so it's not the same. And if you want to have AB the same as BA, then we will call it simply as undirected graph, so the direction doesn't really matter here. Also, there is the asimple graph, and this basically means that each pair of nodes or vertices in a graph are connected through only one edge. So if we observe any pair in this graph, for example, BC, they are connected through one graph. Also CF, they are connected through one direct graph, and so on and so forth. And the opposite of that is a multigraph which has cycles. For example, if we see here, BC have two edges between them, and that way it's not simple anymore, and we call it multigraphs, which has cycles or double edges as well. For example, this is called double edge, and we call it a cycle, for example, if there is a self loop on the node. And one of the most used ones is the weighted graph. Basically, it's the same as the others, and the weighted graph could be also directed or undirected. But in this example, it's undirected simple graph. And it's weighted, so each edge has also a weight, which represents the cost of traversing the edge. Sometimes it represents the time we need to go from node A to node B. In this case, it's 10 seconds, for example. Or it could be also representing the distance, for example, between the node A and node B. There are 10 kilometers or 10 meters or whatever the unit is. And this type of graphs is used in many ways. One of them is Google Maps, for example, and routing. If we see, this is actually my hometown in my home country, Tunisia. For example, if you want to travel from my hometown Bizerte in Tunisia to the capital, Tunis, there are two ways through the car, and Google Maps always suggests the best routing possibility based on time and kilometers, I think, as well. Yeah. And the second application would be packet transfer in computer networks. For example, if we are transferring packets, we always want to use the shortest path possible. So weighted graphs are very highly implemented in when it comes to routing. And surprisingly, even in the nature, we use weighted graphs. So when an ant finds food, it leaves a trail of pheromones, and other ants chooses the path based on the strength of the pheromones trail left by the ant, for example. And this is how they do it. Basically, for example, here we found the food, so the ant goes back to the ant colony and leaves the pheromones trail behind it. So when the others try to get the food as well, they just choose the path with the strongest smell of this pheromones, and just like that, they find the shortest path amazingly. And actually, the ant colony optimization is implemented in many optimization algorithms, and it's classified as one of the heuristic algorithms. Very efficient and very much used. Yeah. And what happened with Euler? Did he just give birth to graph theory and got no credits for it? No, of course, the answer is no. There is a graph named after his name, which we call Eulerian graphs. And basically, they are simple graphs in which the node must have even degrees. So a walk that we can have through this graph could be BCFE and then B. And that way we visited every edge in the graph. Now, okay, different, many types. So do we have different representations for those types? So now, actually, for all those types of graphs, and there are even more that I didn't really talk about. We use two simple data structures, which we covered in our first session, which are matrices and lists. First, we will start with agency matrix, and it's basically as follow. We check, for example, this is a multi-undirected graph. It's multi because we have this cycle right here. If this didn't exist, then it would be a simple graph, but still is undirected. So how we gonna fill this agency matrix? Basically, we check, it's a V by V matrix, with V is the amount of nodes. And for example, we check if there is an edge between A and A. There is no. If there were, there would be a cycle right here. So we just put a 0. And since B has a cycle on it, so B and B has 1 on it. And as we see here, it's a quite symmetric matrix because it's undirected. So BA, it's the same as AB, and that's why we basically get this symmetric matrix. Yeah. And if for directed ones, it will look a bit different. We won't have a symmetric matrix anymore, but rather we will have this matrix. So as usual, if there exists an edge between a node and another, we denote that as 1. If there is no, then we just write down a 0. And here, since BA, it's not the same as AB, if we check the AB, we find it as 0 right here. And if we check BA, it's 1. Yeah. And how do we do it with weighted and directed graphs? For simple graphs that aren't really weighted, we just, if there is an edge between the two nodes, we put a 1. If there is none, we just put a 0. And in this case, simply the idea is if there is an edge between two nodes, we just put the weight as a sign that they are connected, and this is the cost to traverse from the node to the other. And simply like that, since this is an undirected graph, the cost from AB is the same as BA, which is 3. And if we check it in this, again, symmetric matrix, we will have BA as 3 and AB as also 3, and so on and so forth for the other nodes as well. And if it's a list, we use linked lists to represent it as follow. For example, this is a multi-directed graph, and in order to say that there exists an edge between A and C, we just write down that A leads somewhere to C, and also, for example, if there exists a edge between D and B, we just link it and say that somewhere that will lead us to a B, and B is denoted as this X, which means it's a null pointer. So we reach the end of the graph, and also it means that this node actually has no outgoing edges. Yeah, it's only receiving edges and have no outgoing ones. Okay, and then speaking a lot of about many types of graphs and their representation. So what to do with that? Well, basically, we use them in order to implement traversal algorithms. What are these? What are traversal algorithms? Well, it's the process of visiting or updating each vertex in a graph. The sequence in which they visit the vertices is used to classify such traversals. And the most well-known ones are the breadth first search and depth first search, aka BFS and DFS. And those are the most two implemented techniques in graph traversal. Let's start with BFS. Well, BFS logic is basically beginning with a root of graph and investigating all the nodes that the current path has as neighbor before moving to the other level. So we just explore our graph level by level, and each time we see the whole neighbors of the node we started with, and to maintain track on the child nodes that have been encountered. We use it, we memorize it in a data structure, which we also seen last time, which is a queue. And in order to understand how that actually works, let's just see a step-by-step logic. Well, first of all, we just choose a starting vertex, can be randomly chosen, or sometimes it's done implicitly. For example, it says in this problem we will start, for example, with V1 or with the router that has this reference, or with the switch that has this IP address, or so on. So let's say in our case, we will start with the node V1. So we add it to the queue. And then we discover all its direct neighbors. We check the nodes that haven't been visited yet. So we mark them as visited neighbors, and we add them to the queue as well. And then once we are done with all the neighbors of V1, we just dequeue it, because as we seen last time, the queue works with FIFO logic, so first in first out. So since the V1 is the first one that we have seen, it's basically also the first one that will be popped up in queued once we are done with it. And as a third step, we just repeat the process for each node that is in the queue. And in order to implement this algorithm to a code, as usually, I wrote it in Python, and it's as following. We set our queue as empty, and then we also initialize our visited nodes as empty set, and then we start by adding the first node that we are starting with. As I said, for example, we will choose V1, and then we add it also to the visited nodes, and then while there are nodes in our queue, we just pop the first one because we are done with it, and then we print it out as you want. Actually, this is an optional line, and then you just, for each neighbor in the graph for V1, you check if it's not in the visited set. If it's not there, you just add it to the queue. If it's there, you just pass it. And also, after adding it to the queue, you add it to the visited, so we won't double visit later on. Yeah, as simple as that, basically. So, if we see this graph and we want to apply BFS on it, we will start with V1 or 1, just one right here, and then we will explore its neighbor. In this case, we have the 2, and then we explore in this level. We see all the neighbors, and at this time there is only the 3, which has the same level as 2 and is also the neighbor as 2. And it happens that we didn't visit it yet. Then we pass to the next level, which is the third level, and we check all the neighbors of 4, and they are, in this case, 5 and 6, and they are also not visited yet, so we add them to our queue. And at the end, as a result, we have 1, 2, 3, 4, 5, 6 as a BFS result. So the spanning, before talking about the spanning, how does it happen? Basically, the BFS algorithm builds a spanning tree. Spanning, maybe you have heard it from linear algebra, which means we can construct anything from the spanning tree. It has all the nodes that are in this graph and has also some of the edges that are seen in this graph. And as seen, because in BFS we explore the nodes level by level. So we started from 1, then we went to 2, and in the second level we have encountered 2 nodes, and then when we started with the 4th node, we just went deep, and we had these as neighbors. Yeah. Now, how efficient is BFS? And in order to answer this question, as usually, we will use the Landau symbols, but this time I'm not really going to analyze it per hand, but I've brought something original. I've just coded a new web application that analyzes the time complexity of the code. So this is the same code I included in the slides. I'm just gonna copy it and paste it. This is my web application. I'm using Gemini API to analyze the time complexity of codes. Let's just analyze it and see what's, So basically it says the code implements a BFS algorithm. The goals go through nodes of the graph level by level and puts unvisited neighbors of the current node into a queue for further processing, and so on and so forth. And since the graph has 2 sets of nodes and edges, the time complexity is basically big O of V plus E. And it was smart enough to detect the language. I wrote it in Python. And the space complexity is O of V, as we see here. After running the BFS, we have just the queue that at its most will have all the nodes together in it. Now let's go back to what we were doing. So how efficient it is. Its time complexity, as seen, it's big O of V plus E. Now we will pass to the best friend of BFS, which we called depth first search, aka DFS, and it has kind of a different logic. It begins at the root node and check each branch and go further in it as far as possible before backtracking. And to maintain track on the child nodes that have been encountered but not visited yet, we use, as usually, extra memory. And this time it's a stack. We also have seen this data structure in the first week, and the stack works with the LIFO logic, which is last in, first out. Now, let's see a step-by-step algorithm for the DFS. First of all, just as usual, you start with choosing a starting vertex, and then let's say it's V1 in this case, and this time you push it onto the stack. Second, you start finding and using unvisited neighbors, but instead of seeing them level by level, we just go as deep as possible. That's the logic behind it. So we push the neighbor onto the stack, mark it as visited, and move immediately to the next neighbor. And we don't move by levels, we move by depth. And as a third step, we do bytracking. If we are done with the first node that we analyzed its neighbor, we just pop it from the stack because, as said, it's a LIFO. So the last in, first out. If we are done with the node, we just pop it right out and see if we could see any branches from the last node. And fourth, we just repeat the whole process. And again, here it is, here it's kind of logic. So we start with the node 1, we go to the second node, and since the node 2 has also neighbors, we don't go to the level, but instead we just explore the neighbors of 2. So we go to 4. 4 actually doesn't have any edge between it and 5 or any other node. So we reach the null node. That's why we go back to 2, and then we move to the 5. And from 5, we go to 3 and 6 and so on and so forth. So the stack at the end will look like this. So it has 1, 2, 3, 4, 1, 2, 4, 5, 3, 6. The BFS gave us 1, 2, 3, 4, 5, 6, but DFS has different results. And the spanning tree will look also differently because we are exploring the nodes by depth. So we go as deep as possible. As long as there are connections between the nodes, we just keep taking them. And this how would the spanning tree look like? And it looks very different from the BFS. Actually, BFS and DFS spanning trees will only look similar if and only if the graphs are complete graph. So between each 2 nodes, there are, for example, if there are n nodes, so between them it must be n-1 edges. That's that type of graph, we call it complete graph. And in that case, both of the BFS and DFS have similar outcome. Now, similarly, how to implement the algorithm we just saw, or the logical steps we just seen, and how to write them into the code. Basically, I've wrote it also in Python, and it will look like this. We start by initializing the visited set, and we set it as empty. And then we initialize our stack, and we put the starting node, which is which we said as convention, it's v1. And then while stack is not empty, we just pop the last one. And if node is not in the visited ones, then we just print it out and we add it to the visited nodes. And then we just also push it to our stack. And we keep doing that till we have till no nodes are left and the whole graph is explored. Now, how efficient it is, and I will as well use the same tool that I've coded. This is the code for the DFS that we have seen. And if I paste it right here and ask Gemini to solve it for me, it will also tells me that it's written in Python. The space complexity is big O of V, since we are using a stack in which we memorize the nodes we have seen, and also the set of visited nodes, which has also at max V nodes. And yeah, it says that, okay, this is a DFS and it traverses all the nodes, and its time complexity is big O of V plus E. So just like the BFS, they both have big O of V plus E. And actually, they are all the BFS and DFS also are used to check the connection of the graph, of a graph is connected or not. So we use them as well to do that. Now we have spoken and mentioned how important the weighted graphs are and how they have many applications. So can I use the BFS and DFS in weighted graphs? Because the graphs we just saw simple ones without any weights. And the answer to this question is yes, with some limits. So it's basically no. Yeah. So when to use BFS, DFS in weighted graphs? BFS ignores age weights and simply explores nodes level by level. And it will find the shortest path in terms of numbers of edges, but not necessarily the lowest cost path if weights are involved. And similar to that, the DFS also ignores the edge weights and just explores as deep as possible. And it does not guarantee finding the shortest path or the optimal one. So, but it's used just to, in the sake of finding a path, finding a way out, and it's basically used in the labyrinth. So when we are in labyrinth or maze and we just want to find a way out, to escape, we just use the DFS. It's the best way to have a fast solution, but not an optimal one. So, what to use in weighted graphs? Well, you can use the BFS and DFS if you just need to traverse or search the graph or check its connectivity. Or if you want to seek the optimal shortest path, then you have to use the Dijkstra algorithm for non-negative weights, or the Bellman-Ford if the weights are negative, or some of them are negative actually. Yeah, this is it. So basically, that's it for today. Thanks so much for your attention. We have covered quite a bit, from Euler's foundational work in graph theory to understanding how to represent graphs and traverse them. I hope this gives you a solid foundation for understanding graph theory. And I hope you are excited to see what we will explore next. And next week, we will see dynamic programming. So if you have actually questions about it, just tell me to include them in the presentation, since dynamic programming is a big field with many applications. So right now I'm kind of lost which topics to tackle. So if you have some questions, make sure to send them to me so I can discuss them in the next session. And thank you so much for your attention. And this is, as usual, the QR code, so you can connect with me and send your questions or your feedback as well. If something is not really working well, or I should focus on other topics rather than others. And yeah, just be harsh on me. I love feedback. It keeps me growing and correcting myself. Thank you so much for your attention, and I will leave you to Anna right now. I'll stop sharing.